Fatima for the introduction. Come on, this doesn't work. Hold on. Yeah, I think. Okay, I will see how far I can get from my computer to still get this to work. Hold on. This is a very practical. All right. I hope you can still see me. So, a quick overview. I'll give a quick introduction, introduce the current state of the art in glioma segmentation. So, since the work of Matthew, we've already developed a little bit. I will present about segmentation in clinical practice, the way we've done it in Erasmus MC. Some practical considerations, because the purpose of this session is to teach you all to segment glioma yourself. A demo, and of course, time for questions. So a little bit about me. I studied at TU Delft, applied physics and then computer science. I'm now doing a PhD at Erasmus MC Rotterdam about longitudinal analysis of low-grade glioma, of course, focusing on imaging. And you can ask me about machine learning, tumor growth modeling, and of course, glioma segmentation. And that's where I work, in the beautiful Erasmus MC. That picture below is not where I work, that was on vacation. So why do we need segmentation? Maybe this is a trivial question, but I think there you can separate basically two purposes: volume measurements or region of interest selection. And based on what you want, you might have different methods that you want to use. Yeah, so let's talk about the current state of the art. So what can we segment? I think currently we can pretty well segment contrast enhancement, hyperintensities on T2 flare, and necrotic or cystic components of the tumor. What we can very much not segment, at least not automatically, is the difference between tumor treatment effects and of course tumor versus vasogenic edema. Where do you draw the line? This is the question that you are all supposed to answer. I will get a little bit closer to my computer. So the most important recent publications, first of all, of course, the BRATS challenge, which has passed a few times already today. Since the BRATS challenge, everyone and their mother is doing glioma segmentation. So I think there are like 250 publications per year or 300 publications per year about glioma segmentation. So this field moves quite fast. What I present today might have become irrelevant 1 year from now. But in 2019, there was a presentation, or there was a paper from Heidelberg about HD glio, and HD glio is based on a different data set. And this has the main purpose, I will introduce it later, for volume measurement and not so much the BRATS challenge, which is based on mostly radiomics. And in 2020, the BRATS toolkit was published, which is basically the result of years and years of BRATS challenge, which has software for pre-processing, but also a combination of all the winning algorithms to then actually do the segmentation in your own data. So in general, methodology, I'm just going to, of course, every method is different. As I said, there's like 250 new methods per year, but most people use deep learning and they apply a UNet, and they take as input a T1 weighted image, a T1 weighted image post-contrast, a T2 and a T2 flare. Then they throw deep learning at it, and in the end you get a segmentation. For the BRATS challenge, it has 3 different parts. So there's edema, contrast enhancement, and the tumor core or the cystic or necrotic component. And so this deep learning network is trained on data. So whatever you put in, you're going to get out. So that's why from now on, I'm going to completely disregard the deep learning method underlying, just look at the data. So, as I said, there are generally two important data sets in the field of glioma segmentation. On the one hand, there's the breadth dataset, which is the most often used. This is only preoperative imaging. In my experience, it doesn't work very well on postoperative imaging. There's 3 classes, as I introduced. The latest edition, which was finished, like the last breast challenge ended yesterday, has 2,000 cases, which is a great improvement with respect to last year when it was like 400-ish. I haven't seen the results on performance yet, but I think I've seen a few papers. I don't think the performance has increased a lot with the addition of over 1,000 new cases. But the main thing about the breadth challenge is, of course, that the data is available. So you can use it to train your own model to do exactly what you want to do. But in general, the purpose of the breadth challenge was radiomics. So to use the results of the breadth challenge to then, or the segmentation, to then, for example, predict IDH mutation, MGMT methylation, whatever you want to do, survival prediction. And of course, there's many implementations that use the data from the breadth challenge for tumor segmentation. Then the other important data set is the HC-Glio data set. And this is a longitudinal study. So this has mostly, I think, post-operative imaging. It segments only 2 classes, so it only looks at the T2 flare hyperintensity and contrast enhancement. Necrotic core isn't segmented. But for this implementation, the data is not available. So you will just have to trust the authors that they did the right thing, and you can't train your own method on it. But the model is available, so you can use it. And since I work mostly on postoperative imaging, I'm going to talk mostly about HC-Glio. So next, segmentation in clinical practice. So I'm going to talk about the work that we did in Erasmus MC. We implemented automatic tumor segmentation in the clinic, specifically for volume quantification in adult low-grade glioma. So very practical overview of the software that we use. So images go from the scanner into the PACS. Then from the PACS, the radiologist can segment imaging, can select imaging and send it to the system that we call EASE. EASE is Erasmus Automated Segmentation. And then they are stored on an XNAT locally on the system. It goes into the segmentation pipeline. The segmentation pipeline uses HC-Glio. And then there's an interface for annotation so that the segmentations can be checked by the radiologist. And then the results go back to the PACS. And we developed a clinical protocol for the usage of these segmentation results because, of course, we cannot guarantee that every segmentation is always correct. So in order to be allowed to use this in clinical practice, we had to develop a proper protocol for the usage of these results. So for one diagnosis, the radiologist will always use 3 consecutive scans. This is also the case without segmentation. And we made sure that first the radiologist has to make a diagnosis based on their conventional method, so without EASE. And they do that on a 2D, based on the 2D measurement, if they can measure. And then the segmentations can be checked in EASE, and radiologists had to decide for every segmentation separately whether it's acceptable or not acceptable. And if one of the segmentations has failed, then there can be no volume diagnosis because there is not enough results, of course. But if all 3 are successful, these results go back to the PUCs, and the radiologists can see the volumes and then make their 3D volume-based diagnosis. But if this leads to a different conclusion than their initial method, the conventional method, they have to go to a second rater for consensus diagnosis, just to make sure that with this new measurement tool that they have, they don't make mistakes, basically. So this is a view of the annotation interface. So it shows 2 screens where the radiologist can change between the different sequences. I also made sure to include the volumes to make sure that radiologist doesn't miss some false positive. Sometimes there's a part segmented on a completely different part of the brain, and I don't want them to miss that. And then the radiologist says whether it's acceptable or not acceptable. And we also included a quality rating going from 1 to 5, just to keep track of how the system is performing over time. And they can add any comment that they want, which will be included in the final report. And then a report is sent back to the PUCs. It's just a PDF that includes the patient information, segmentation results, processing information, the version number of the system, which is very important, because if we make any changes, then we want to know which version was used for the segmentation. And the actual segmentation is also made into a DICOM and sent back to the PUCs. So they can always look back and think, I see volume measurements that I cannot explain. They see the segmentation and maybe they think, this was a bit over-segmented, so it makes sense that maybe the volume decreased. And of course, we evaluated the performance of our method in clinical practice, for which 55 patients were evaluated with ease. Out of those, 36 actually had 3 successful segmentations, so that's just over half of patients could be diagnosed with the system. But we did notice that although a lot of these cases had a successful diagnosis, in some cases volume measurements are not completely consistent. They can be a little bit misleading. And I will show you why. So HC glio, and I think also for breaths this is probably also the case, they are very sensitive to the intensities on T2 flare. And maybe this is just in our clinic, but our T2 flares sometimes change a little bit. So depending on the intensities on the T2 flare, sometimes it might be a little bit over-segmented or under-segmented. And because, of course, the border of the tumor is a little bit subjective, the radiologist might accept all of these segmentations thinking it's all right. But then when you compare them, especially in low-grade glioma, which can be quite small, very often you get a big increase in volume just due to changing the boundary a little bit. So in some cases, this will happen. That's why it's very important that the actual segmentation is stored in the PUCs, so the radiologist can always look back and think, okay, I see a volume increase, but actually this is due to the segmentation being a little bit different. So here you can see on the top an example of this change in the segmentation boundary between 2 consecutive scans. And on the bottom, of course, I also included a segmentation that is actually consistent. In both cases, there isn't any significant growth in the tumor. We also compared the 3D volume measurements to the existing 2D measurement method, which is the Rano criteria, where you take 2 perpendicular cross-sections. And I have to say that this was performed after the study. So this wasn't actually measured in clinical practice because most of these tumors are not measurable because they are just so strangely shaped. They're not circles. So in this case, the measurements were taken at the part of the tumor that could be measured best. Actually, it correlated quite well with the final diagnosis. So in this figure, you can see which cases were diagnosed as progressive disease and which cases were diagnosed as stable disease. And in some cases, you can see that this volume measurement has some outliers that are just due to segmentation inconsistencies, whereas the 2D Rano method is actually quite well correlated with the final diagnosis, which can also just indicate that radiologists, despite the fact that they have access to this volume measurement, still rely on their 2D visual inspection. So in conclusion, we can apply automatic segmentation and volume measurements in clinical practice if we use the proper protocol and quality checks to make sure that no mistakes are made. The performance, we have to say, was slightly disappointing. We expected a little bit better acceptance rate, but is likely due to patient selection. So low-grade glioma are relatively difficult to segment. And could also just be to the differences in scan protocol in our data with respect to what the HT glio method was trained on. And a big point of interest for the future is to improve longitudinal consistency. Of course, when the radiologists make their diagnosis, they actually look at longitudinal data. So they take that into account, whereas the segmentation methods always rely on one instance. So maybe if we can include the entire longitudinal data, we might improve the consistency. And of course, acknowledgements, my group, my supervisors, Marion Smith and Stefan Klein, and a lot of collaborators. And we have a picture of our group. And then I would like to go to questions before I move on to the more practical part of my talk, which will be a demo and a short discussion of pre-processing. And I will move here.
Thank you very much for the very nice, clear, and informative presentation. Is there any question from the audience? I can start my question. So my question is that if we want to look at this longitudinal analysis of brain tumor segmentation, so then the first thing that comes to my mind is that how to register them, because tumor change, and it's like a lot of issue with that. Would it be possible? Do you see any future in this?
Yes, so I said it very simply. We have to look at longitudinal data. Of course, this raises a lot of issues in terms of bias and registration. So this is not a simple quest. But we'll see. I think we can develop the methods. It might take a little bit of time.
I do have another question. So you mentioned quality, consistency. Maybe this is what I need to say. Consistency between the flare scans you need. Do you know, because I know in a center like ours, patients will not be scanned on the same system, probably. Is this something that you would say, make sure you do that, or just invest a lot in making sure you have the contrast? Like, what would practically be your advice on these kind of issues?
Well, if you can make sure that everyone is scanned with the same system, then you should definitely do that. I am usually not in a position that I that I can change that. I always look at retrospective data. So then there's probably a lot in terms of pre-processing that we can improve to make the flares, for example, more consistent, which I will look into because I have this problem in my study as well. But if you can fix it at the source, you should always fix it at the source.
I don't see any hand raised, but I think we can now move to the demo session.
Yes.
So stay with us, and yeah.
I will have to do the demo from my laptop, so you will not be able to see me. But first, okay. I have a few slides still, and I noticed that I can't talk over there. but can you put up my screen again? Yeah. Yeah, so I'll start with a little bit of presentation again. So practical considerations for Glioma segmentation. Pre-processing. There's a few steps that you have to take. In general, there's of course systems that do the entire processing pipeline for you. But in general, these steps include registration, skull stripping, resampling sometimes, bias field correction if you need it, and segmentation. A few tips. So for registration, this is just a rigid registration of the 4 modalities. And you can pick, in general, any reference space, so pick that carefully. I usually register everything to an atlas first, but that just depends on what you want to do with the results, because of course your segmentation results will be in that reference space. Skull stripping. I have seen a few questions about this already after Matthew's segmentation presentation, I mean. I use HDBet, which is a relatively new method. I will also show you in the demo. It works, in my experience, a lot better than any existing method. Resampling, so this depends on which method you use. HDGlio doesn't require resampling, but the Bratz data set is resampled to 1 millimeter isotropic voxels. Bias field correction, you only need it if the bias field is visible. So in our data, sadly, we do have to do bias field correction, but so that depends on your scans. And then practical issues for segmentation usually require a GPU, which is a bit of an investment if you don't have access to it. But there's really no fix for that. I think there's no method available that works well, that doesn't require a GPU. But of course, you can look at Bratumia if you really don't have access to one. A small practical tip, if any one of you wants to start working with HDGlio, make sure you install PyTorch first through the official installation instructions, or else you will be running into a lot of issues, but that's a small practical tip. For checking and correcting segmentations, I heard from Fatima that some people might also be interested in that. I always use ITK Snap, and I will also give a short demo of how that can work. But my general tip for that is look up their YouTube channel and watch their instructional videos, because there are so many things in ITK Snap that you can use that you might not know about. But I also give a short demo. There's also some new integrated software solutions if you want to do the whole pipeline automatically. There's the Bratz toolkit, which does pre-processing and can run a selection of algorithms or a combination of algorithms to get the best results from the Bratz challenge. I hope they will update it after the new Bratz challenge of this year. There's the HDGlio auto method, which is a Docker implementation with integrated pre-processing, which is also quite nice. I cannot use it because my GPU cluster cannot run Docker, so then I have this issue. And I also want to mention the CAPTK software, which has a GUI and has like a broad selection of tools that can run registration and can run skull stripping, and it also has a tumor segmentation and a brain extraction method included. So have a look at that if you really want a GUI interface. And I will do a demo, or try to do a demo. Let's see if this works. Can I talk here? Yes. I think this is all right. So this is a live demo, so it's definitely going to fail. But I hope it's instructional. So first, I've included an example of the Bratz dataset. It's not very well visible, is it? Let me see if I can change the contrast. So this is ITK Snap. It has a lot of useful tools. First of all, what you need to know is how to change the contrast in your images. But I think this is better. So here you can see the 3 classes. And then what I really want to show you, because I only learned this while preparing this demo, by looking at the YouTube channel. Let me unload the segmentation. So, oh. There's a very nice automatic segmentation method in ITK Snap that you can access through this snake icon. I hope you can all see this a little bit clear. So it has a clustering, so I will just go through the steps. You do a region of interest selection, which I've already done. So you take a region of interest that encompasses the entire tumor. Then you can run a clustering algorithm. So it will cluster the data. And this clustering is based on all modalities that you put in. So this method works on anything, not just brain tumors. But it is a clustering of a combination of these modalities. You can add any that you want. And then you select the number of clusters that you think is representative for what you can see in the data. I think there are 8 different types of tissue or types of voxels in this data. So then you can run the clustering, and then it will basically assign a speed image, what they call the speed image, for every voxel for different clusters. So here you can scroll through the different clusters, and probably one cluster will represent what you want to segment. In this case, this is a cluster, I think, of the contrast enhancement. And then there is a cluster. I'm going to look for the cluster that has edema. I think this one has edema. All right. Edema wasn't so well clustered. But let's look at the tumor core. So this is, I think, a cluster of the necrotic core. And then once you have selected your cluster, you add a bubble. And this bubble is basically the initialization of your segmentation. It doesn't have to be exactly within the region that you want to segment, just somewhere inside. And you can add more bubbles if you want. And then you run the segmentation, and it will very nicely segment or fill up basically the cluster. And then if you look at the result, you can look at the 3D representation, and you can see that this is quite successful. And then you finish it, and then you have your segmentation. Of course, it won't always be perfect immediately. So I'm also going to show you how to edit your segmentation. For that, I'm going to look at this part that I don't want to be included. So then there is the brush. I hope for the people at home it will be more clear than for the one sitting here. But you can do a 3D adaptive brush. So this is an adaptive brush that will basically, you click it and it will try to adapt to the image intensities. And then you can use that. So you can remove, but you can also say you want to segment the ventricle. Then it will adapt to the intensity. So here you can see that it follows the borders. And if you want, it can also, if you choose the 3D option, it will also propagate to other slices. So this is a very nice tool. If you have never seen it and you want to do manual segmentations, I can recommend this. Then let's look at HD-BET and HD-GLIO. So for that, I have to connect to our cluster in Erasmus MC. I will try if I can zoom in a little bit. So this should be a bit more visible. I have some data here. And I have an example from the BRADS data set and some examples from our clinic. I'm going to first start with HDBet. HDBet can run with a GPU or without a GPU. This system has 2 GPUs, so I'm going to run it with it. So without GPU, it will just be very slow. And so to run HDBet, you have this command. It's just called, so once you've installed it, it's a Python package. You run HDBet, you enter the input folder and an output folder. And it will basically find any nifty file in your input folder and try to perform skull stripping on it. And the output will appear in the output folder. And while it runs, it does a little bit of pre-processing, and then it applies to CNN. It applies a number of CNNs and then combines the result. And I'm going to show you the input that I put in. This is the output. So this is what I put in. This is some data from our center. Low-grade glioma, the difference. So this is registered, but not skull stripped. This is what I put in. And this cluster doesn't have any visual interfaces. So I also already ran the demo before, and I will just show you the results. This is the output. Let me take away the segmentation. So in my experience, HDBet basically always works, but there's always a few exceptions, of course. So of course, for this demo, I selected the one case that might fail. So in this case, in the folder, we had these 4 images, and they were all very nicely skull stripped, except the T2. So there was an error here. But okay, so usually it works with a few exceptions. And then I will also show you the results of HC glio on this data set. And for this, I can already show you the limitations of HC glio. Of course, I'm a bit biased towards low-grade glioma, so I only know the limitations specifically on low-grade glioma. But you have to always be careful of the fact that HC glio segments hyperintensities on T2 flare. So in this case, if not all of the tumor is actually hyperintense on T2 flare, because this case has a lot of tumor here that we can see on T2, but not on T2 flare. It will only segment the part that is on T2 flare. So that's one limitation. But so I'm only going to show you the things that fail, but usually it works really well. Yes, so this is finished, and it's very difficult live programming while holding a microphone. So to run HC glio, there's 2 commands. There's the HC glio predict folder, and there's the HC glio predict. But to run a folder, you can just put all of your imaging in one directory. And as long as you did the naming correct, it will work. So so you basically have to name all your images with an identifier and then 000 or 001, 002, 003, which is T1, T1 post contrast, T2, T2 flare. And then you can run HC glio predict folder, and then it will just do all of the. So, and if you have multiple, you can dump all of that in one folder, which is very useful if you want to run a pipeline on a large batch of data. And then I wanted to show some output. Yeah, so one thing I wanted to show you is that, again, about the T2 flare, it's very sensitive to pre-processing. So in this case, I have 2 examples. And it's the exact same data, The difference is that in one case, I did skull stripping on the T21 post contrast and then applied the mask to all the other modalities. In the other one, I did skull stripping individually for all the images, so that's this result. But you can see that the result of the mask is slightly different for the T2 flare, which you might think is quite irrelevant, but it produces a very different segmentation. So this is the result for the skull strip part for this data set, so skull stripped individually. And this is the result for taking the brain mask from the T1 post contrast. So be aware that this makes a large difference. Of course, we can argue about which segmentation is the best, but I just recommend trying it out for yourself on your own data. And we can see that the segmentation was successful. So I think this was everything that I wanted to show. So I think the best thing to do is to just now have a little bit of a discussion.